Okay, guys, this quick lesson is we're in 1-6, and again, 1-6 sprinkles into 1-5 when you start talking about intermolecular forces. So, we're talking about like comparing strengths of different substances, compounds, elements, that kind of thing. And by strength, I mean like if they were in a solid structure, how much energy would be required to melt the structure, the solid, into a liquid, and then maybe even vaporize it into the gas. So really what we're talking about is the strengths of the intermolecular forces. Now, the problem with saying the strengths of the intermolecular forces there is really intermolecular forces when we talk about like hydrogen bonding, dipole-dipole interactions, London dispersion forces. That generally is, we're only talking about covalent compounds there, and we're talking about actual molecules. So it's got to be a compound, not an element. So molecules of that compound interacting with each other. And so for it's got to be a covalent molecule. It could be a big molecule like some organic structure. But when we start talking about, why is sodium chloride's melting point so much higher than water's melting point or something like that, and we start talking about different types of compounds now, so not just covalent, we start talking about ionic compounds, so salts, or just metals, like in general, like why does gold have such a high melting point, or why are most metals solids at room temperature, meaning they have kind of strong, and again, the word wouldn't be, the verbiage wouldn't be right to say intermolecular forces when you're talking about a metal structure, because metals, the smallest unit of the metal isn't a molecule. The smallest unit of a metal is the atom of that element. And so it would be like what interactions are happening between the atoms, right? So it would be interatomic forces, right? So you want to be careful in just always saying intermolecular forces when you're talking about differences in boiling point, melting point, that kind of thing, because you might not be comparing apples to apples. You might not be comparing covalent molecules to other covalent molecules. If I'm comparing covalent molecules to other covalent molecules, then yeah, I'm going to be looking at the intermolecular forces, the traditional ones, hydrogen bonding, dipole-dipole, London dispersion. But if I'm looking at a salt, if I'm looking at an ionic compound or a metal, or there's something else that actually has a pretty strong structure as well, which we'll talk about, it's different types of forces, but it still kind of comes down to Coulomb's law, especially for those ionic compounds. So we just need to learn how to talk about it a little bit differently. That's it. All right. And so what we want to be able to do is answer a question like this. All right. So given a list of different substances, so, some of these things are ionic, some of these things are covalent, some of these things are maybe new to us that we haven't really got into yet. And then like here is a metal element, right? So we got a bunch of compounds, but then we have this element over here, calcium, a metal. And we want to rank these from, highest boiling point to lowest boiling point, or highest melting point to lowest melting point. So really what we're saying is the strongest structure, right, to the weakest structure. That's really what we're trying to rank these, okay? Now, make sure you don't use Google, because what we're going to learn some basic rules, the rules of thumb to follow. But, as we learn in chemistry, there's always exceptions, right? So the ionization energy trend, there's exceptions to that, right? Electron configurations, following the periodic table, there's exceptions to that. So there's always exceptions. So yes, if you wanted to answer this question, you could Google all of these guys' melting points and rank them in that order. But, if this were on the AP exam, and you probably wouldn't get a question with this many different things to compare on the AP exam, because it would just be kind of too time consuming to waste on kind of one topic. But, if you're given this, you have to think of what you have at your disposal. You have a calculator, and you have a periodic table, and you have a formula sheet. Okay, that's it. You can't Google it, right? So you just got to go with these basic rules. So when you're doing the one in Schoology, make sure you're not Googling the answers, because if you Google it, it's going to be out of order from the actual answer that I have, because I'm not using Google. I'm using the information you're supposed to know, and that's it, without looking it up. All right, so make sure you do that. All right. So the notes you want to review are the types of compounds in IMF review, because this is first going to tell you the order to first, differentiate the compounds. So if you're given a list of different things, the first thing is look for a network covalent solid. Okay, so we're looking for silicon dioxide, solid silicon, or solid carbon. That's what we're looking for. If we have one of those, we're going to assume that's our strongest structure. We call those network covalent compounds. Network covalent, and carbon would be a network covalent element. It's not a compound. But those would be top dog. They have very strong structures. Like you probably hear diamond is the hardest thing. Well, it's because it has a very strong structure. Now, graphite can slide off of your pencil, right, with pressure, but it takes a lot of energy to melt graphite. So there's something, graphite is just carbon, diamond is just carbon, but the structures of the two solids are different, but they are still called network covalents. And so they're going to be very strong, right? So after you find if you have a network covalent, the next thing to do would be look for ionic compounds. And we're going to assume that all ionic compounds are going to have higher melting points than any metallic elements, and then any metallic elements have higher melting points than any just regular covalent. And then if we want to separate the covalent compounds, we could have polar covalent, non-polar covalent. And then if we want to separate the polar covalent, you could separate it into, is it polar with a Fon bond, so it has hydrogen bonding, or is it polar without a Fon bond, so it just has dipole-dipole interactions? And that's how we're going to rank them. And again, this is without using Google, all right? So that's the first thing. So if we go to this question that's on your practice quiz, notice silicon dioxide's there. So I know that's going to be number one on my list, silicon dioxide, all right? Now let's look for any, so if you got a question like this, they wouldn't give you two network covalents because they'd have to give you more information to determine, what has a higher melting point, quartz or diamond, right? You don't need to memorize those off the top of your head. So they would only give you one network covalent, right? So SiO2 right there. Now we're going to look for our ionic compound. So that's an ionic compound. There's an ionic compound. And there's an ionic compound. So these are going to be our next three. All right, so we're going to assume all ionics are going to be the next highest. So for ionic compounds, you're going to look at the size of each ion in the compound, and you're looking for smaller ions because smaller ions can get closer to each other. That increases the Coulombic attraction. Or you're looking for higher charge as well. But what we're going to notice is lithium's +1, fluoride's 1-, so this is +1, -1. Lithium is +1 again, and chloride's 1-, so +1, -1, and this one is +1, -1. So the charge is not going to be a factor here, it's going to be the size. All right, and so what we have to understand is lithium is a smaller ion than potassium, and fluoride is a smaller ion than chloride. So these ions, the lithium fluoride ions, are going to be able to, the lithium and the fluoride ion are going to be able to get closer to each other than these ions and then these ions. So that's going to increase the Coulombic attraction, increasing the strength of its lattice structure or its structure. And so I know LiF is next, followed by LiCl. Why LiCl? Because I know that lithium is smaller than potassium. So the lithium ionic radius is going to be able to get closer to chloride's ionic radius compared to potassium. So this would have the next highest Coulombic attraction, and then it would be the potassium chloride next, right? So after that, we're looking for metals, all right? So we got water, we got chloromethane. All right, here we go. We got a metal, calcium. All right, and we only have one metal, so that's going to be next on our list. If you were given two metals, let's say you were given a transition metal, and an alkaline earth metal like this, the transition metals tend to have stronger structures. So like the heavier metals in the D block are going to be stronger than any of the metals in group 1 or 2. All right. So that would be the next one. And then now we're looking at just regular covalent. And remember, organic falls under covalent. But we're looking for polar first. So this guy, water, we know is polar, so I'll highlight that. So we know that's polar. And this would be polar because the ligands are different, so I'll highlight that. But the methane and the carbon tetrafluoride, those would be non-polar because they're symmetrical. Tetrahedral, same ligands, tetrahedral, same ligands. This one's tetrahedral, but different ligands, so polar. Okay. We're going to go with water next because it's polar with Fon bond, so it would have hydrogen bonding, whereas the chloromethane would be polar, but not. It doesn't have a Fon bond, so it would just have dipole-dipole interactions. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, okay. So we got 9 things, and I got 10 spots. Sorry about that. So we're only going to 9. And so the next one would be these two guys. They're nonpolar. Their strongest IMF is London dispersion, and London dispersion is determined by the number of electrons. So CF4 has more total electrons than CH4, so we would expect the London dispersion in CF4 to be stronger than the dispersion in CH4. Okay? And so that's kind of how you do it. I'm going to do an example on a Schoology assessment. So here, let me see if I can make it a little bit bigger so you can see. All right, so we got a bunch of things, and we want a highest melting point to lowest. So highest melting, so strongest structure on top, lowest. So again, let's do this. Let's see, do we have any network covalence? Yes, we do. We have carbon, so that's moving up to the top. Okay. Now let's move all of our ionic compounds up to the top, and then we'll put them in order the proper way here. Okay, so is that all the ionic compounds? Yes. Okay. So, so for the ionic compounds, we need to know that lithium is a little bit smaller than magnesium 2 plus, and oxide would be a little bit smaller than chloride 2 plus. So this is a +1 attracted to a -2, and this is a -1 attracted to a +2. But because these two ions are smaller than those two ions, we'll move that up to the top. Then if we're comparing magnesium chloride to sodium chloride, we got two things going on here. We should know that magnesium 2 plus is actually smaller than sodium 1 plus, right? Because they have the same electron configuration, but magnesium has one more proton. So magnesium has the smaller ionic radius there. And it's 2 plus attracted to 1 minus, so that's going to be a stronger interaction. So magnesium chloride would be next, followed by sodium chloride. Now we're looking for any metals, and we only have one, so zinc, so that'll be the next thing. Now let's look for our polar molecules. I know water's polar. I know pH3 is polar because it's pyramidal shape. I know PF3 would be polar because it's the same shape. Okay. Now, I would go with water because it has a Fon bond, so it has hydrogen bonding. I would put PF3 above PH3 because I would say that PF3, the PF bond is probably more polar than the PH bond. So this dipole-dipole interaction is probably stronger than that dipole-dipole interaction. But the tipping point would be the London dispersion forces. This would have more London dispersion because fluorine has more electrons than hydrogen. Now, okay, so we would assume PF3 then PH3. Now, if you're using Google, you might notice something that's not correct about that, but you're not supposed to. So the thinking should be this has a stronger dipole-dipole interaction because it's probably more polar, and fluorine has more electrons, so greater London dispersion. All right, and then we have the nonpolar things, and they're already in the correct order, right? Nonpolar, nonpolar, nonpolar. This has more electrons than that, so greater dispersion than methane, and then methane has more electrons than hydrogen. So hydrogen, only 2 electrons, not much dispersion there. So that would be the weakest. So this would be the order I'm looking for that question on your Schoology assessment. All right. So hopefully you kind of understand the reasoning. And don't forget to watch the other 1-6 video, just going over what this different solid structures kind of look like on the particle level. Get used to those types of diagrams. But yeah, so hopefully that helps. And yeah, so, we're pretty much wrapping up all of this stuff in Unit 1. You got Concept Check 3 you could be working on. You got the 1-5, 1-6 assessment. We're going to do official guided notes on this stuff coming up, and then we're going to have a lab where you have to use some different tests to identify some solids, and then we're gearing up for our unit test coming up. So make sure, if you're feeling confident about all this stuff, make sure you're starting to look at the test review materials that are posted. And all right, have a good one.